Coming back to another lecture on Z transforms of discrete time sample data control systems. So in this lecture we would look into the Z transfer function, which is also called the pulse transfer function. So let us see this. So when we have understood the Z transform of a signal, and we have understood the concept of a sequence of values being treated as signal. So this is basically the sampled signal can be treated as a sequence of values. So now we can treat this as a discrete time signal, discrete time input sequence Rk, and say that such a signal is getting applied to a linear discrete system and producing an output sequence Yk. So here this system we are not assuming to be continuous time, we are assuming this to be linear discrete system. So this is also a discrete system. So it accepts, so it is a discrete system, it accepts discrete signals and it gives out discrete time signals. So it accepts a sequence and gives out a sequence. So such system are linear discrete system. So it is a mathematical convenience that we are assuming the system like this, and we would like to understand what exactly is the representation of such a signal, such a system. So when Rk is equals to the delta k, which is the impulse, then the output sequence is the impulse response Hk. This is also called the waiting sequence. Now if we excite the system with a delayed impulse by a delay of d, the response is also similarly delayed, and the response is Hk minus d. Why? Because the system that we have considered is causal in nature. So the causality is an important assumption, and which is a very basic assumption for all systems that we deal with. Causality means if you have a signal, so this is the input Rk, so this is your impulse, Rk, Yk. So if you give an impulse, you will get a string of values, or if I write if I denote them as impulses, something like this I might get. Okay, finally it might die down. Now if I take a delayed impulse Rk, I take it here, then the Yk would also start from here, and this same sequence. So this is a causality thing. That means the system cannot anticipate what particular input signal is coming to the system. Only after the application of the input signal, the system will get excited and give a response. What is the pulse response? The pulse response is a response of a string of pulses basically. So here what we do, we we represent the input sequence Rk as a sum of delayed impulses, like this. So you know that Rk is having these values R0, R1, R2, etc. Now we can say that R0 is basically R0 delta k, R1 is basically R1 delta k minus 1, R2 is R2 delta k minus 2. The string of impulses which are delayed by 1 unit of time. So there was, for only the impulse, this is only R0, but now we have another impulse here which is having strength of R1, here which is having strength of R2, here which is having strength of R3, like that. So it will go on. So the entire sequence can be represented as a sum of delayed impulses, and the response to this, so this is response to any particular signal delayed by m will also be that this is a weighting, this is the weight of this impulse. So this weight will remain same, and whatever response delta k minus m was supposed to excite, so since delta k was exciting hk response, delta k minus m will excite hk minus m response, and you see that this hk minus m is a string of pulses itself. Hk minus m is a string of pulses itself. For a single pulse here, hk minus m is a string of pulses, but will have a weight of Rm also with it. So this is the response of each pulse. So this is at delay m, suppose. So this is the Rm, and this particular signal will excite this output. Now since this is a linear system, so many inputs are we know the output of for each of these input. So the total output will be the output due to the total input will be the equal to the summation of these outputs. So yk, which is the output sequence, will be the summation of Rm hk minus m. Okay, Rm hk minus m from m equals to 0 to infinity, 0 to infinity, it can go on till infinity. However, you notice that for k for m greater than k, we cannot have any value, because your for k less than m. So here you see, here you note, so this is the output which is starting at m. For k less than m, this region, for k less than m there is no output. So your hk minus m is 0 for k less than m because of causality consideration. Hence you can abruptly end the summation at k. You don't need to take it to infinity, you can end it at k. So this is a very important assumption. If causality was not assumed, we will not be able to do this truncation of the summation, and this truncation is important. This actually now you see here that if you take the Z transform of the output sequence, if you take the Z transform of the output sequence, then this YZ will be the, so this is the output sequence, this entire thing within the bracket is the output sequence. And if you want to take the Z transform of the output sequence, you have to put a summation from k equal to 0 to infinity along with a Z to the power of minus k weighted with this signal. Now you can take this Rm out and change the order of the summations, and then you assume j to be k minus m, and you will get this particular result. So if you assume j equals to k minus m, your k will be j plus m, and you will have your z to the power of minus j this side and z to the power of minus m you bring this side. So this particular thing you see, it is rz, and this particular thing is hz. So yz becomes equals to rz hz. What is rz? Rz is the Z transform of the input sequence. So you have a relationship between the Z transform of the output sequence and Z transform of the input sequence related through the Z transform of the impulse response. This H k was the impulse response. So this is a transfer function now, because it relates the input and the output. It is input by output, and this is the impulse response, z transform of the impulse response, and is called the pulse transfer function or z transfer function of the linear discrete system. Of course, you can note that when the input is delta k, Rz is 1, and hence your output is the pulse transfer function, basically the z transform of the unit impulse response. So another idea is this, that Rz and Hz, this multiplication is commutative in nature, hence and if you pass through two particular systems, two LDS having their pulse transfer functions Hz and Gz, then they can be combined together to you can combine these systems to one system which has a z transfer function Hz Gz. So this is similar to the Laplace transform, so similar to the normal transfer function is in S domain. Now we analyze the system using the idea of z transform and pulse transfer functions. We analyze a linear time invariant discrete time system. So suppose the time invariant discrete time system is described by difference equations. Difference equations are these equations which you are seeing here, where the output there are these signals which are delayed instants of output. Okay, outputs with delayed instants as well as scaled by some coefficients. Okay, so this is the difference equation. So output at one side like this and input at another side like this. This Rk is the entire input sequence. Please keep this in mind. This Yk is the entire output sequence. Yk minus 1 is the entire output sequence delayed by 1 unit of time, and there is a pre-scaling of A1 to this entire output sequence. Similarly, B0 Rk, B1 Rk minus 1 up to Bn Rk minus n. And now you can take a Z transform on both the sides and considering zero initial conditions and remembering the property that the Z transform of Yk minus 1 is basically Z minus 1 Yz, and similarly for all these delays. So you get this particular equation, and from this equation it is very easy to find out the Z transfer function or the pulse transfer function for this difference equation. And it is simply you note that it is simply the coefficients of the input side by the coefficient of the output side, and you can represent it in terms of powers of z minus 1 as well as in powers of z, both is fine. So here we have expressed in powers of z. This is the most used form, expressed in powers of z to the power of m minus 1 up to 0 and zn n minus 1 up to 0. So the previous one, here we had delayed the input and the output by the same amount of time. However, the input delay has to be less than the output delay in order to get a proper transfer function. So for the proper transfer function, for a proper transfer function, this input must be less than the output. Now what we are doing here, basically we are considering that this is the output itself. Okay, so some output we are considering which is in the form of numerator by denominator, and we are trying to see what is the uh, what is this output sequence yk, what is the output sequence yk when the z transform of the output is in the form of a numerator by denominator form like this, which is proper, a proper numerator by denominator form. We have yz, then what is the output sequence yk? That is what we are trying to find out. Here we can divide this numerator by the denominator, and what we will actually get, we will get a sequence with different coefficients of in the powers of z to the power of -1. Basically we will get a sequence with powers of z to the power of -1, -1, -2, like that. And you know that if yz is like this, that means the sequence yk you have been able to extract out. The yk sequences are y0, y1, y2, like that. An example you see in the right hand side, suppose your yz is z square plus z by z square minus 2z plus 1, and if you divide, then you will get a infinite sequence like this. So you can perform the polynomial division for yourself, and you will see that you get an infinite sequence, and the first few terms of this sequence has been written down, and this will be now your y0, this will be your y1, this will be y2, like this. So you see we have written down y0, y1 like this. However, the disadvantage of this method is that you don't get a general form yk. Yk equals to something in a function of k, and and those things. So you don't get a general yk. You can point out what your y0 will be, what your y1 will be, as such what exactly your y100 will be, you can point out, but you will not be able to get a general yk formula. To do that, one has to come to this sort of a representation where you are breaking the yz down into partial fractions. But for this you have to know the roots of the denominator polynomial. You have to know the roots of the denominator polynomial, otherwise you will not be able to do it. So anyway, supposing we are able to do this, then we have to note that 1 by z minus a in general can be written down as z inverse z minus a, and z minus a inverse Laplace transform, inverse z transform is a to the power of k, and since there is a z minus 1 in front of that, this becomes a k minus 1. So you look back into the properties table, and you will find in the transform pairs table you will find that this particular thing exists. So this relationship comes from both the pairs table as well as the properties table. So both table you have to refer once in order to verify that this thing is correct. And one thing you have to mention, for what values of k this is valid. This is obviously valid for k greater than equals to 1, because for k equals to 0 you don't have your sequence. So here you see that the total sequence then will become, if you take the inverse z transform, it will become d0 delta k, since inverse z transform of 1 is delta k, and the others you are getting this a1, these are all scalars, scaling terms, and the remaining terms you are getting a2 like this. So this is yk, and this k for greater than equals to 1. In case there are repeated roots, we are dealing with one particular example of order 2, then what we do, the factors are obtained as 1 by z minus a square, because you will have to do some differentiation etc., and you will get such higher order factors. So if you get a z minus a square, that is nothing but 1 by a z inverse a z minus a square, and this thing has a inverse z transform of k a to the power of k, and since there is z to the power of minus 1, you have a k minus 1 a to the power of k minus 1. So let us look into one example here. For this particular situation, to apply in this particular mode, you have to divide the denominator polynomial into the corresponding roots, and you see that there is a repeated pole. So and when you calculate the residues of these terms, you will get the residues as 2, 12 and 2. So this calculation is left to you. I hope you know how to calculate residues of these terms. These residues, I hope you know how to calculate, and then what you will get, you will get your yk as this, and you have to mention this thing. If you are you can do it in another way. So if you don't have the d0, suppose the d0 is not there, so if you don't have the d0, then you can actually do it in this manner. So you can take a z out, okay, from the numerator. So this you can actually not this thing. So if you don't have a d0, this is not the correct statement. So if you can actually take a z out of nz, so here you see in this example you can take a z out of nz. So if you are in such a position, then you can take a z out of nz, and then with nz by mz, here you do the partial fraction, and then with every partial fraction you have a z at the numerator. So the partial fractions are in the form a by z minus a. So for every partial fraction you have a z in the numerator, and then you can directly you know that z by z minus a1 is basically a1 to the power of k. So you get this equation. Now coming to the same example that we were working with. So here you take z out, you have 4z minus 2 by this. Now the difference with the earlier case is that the numerator has changed. The numerator earlier was 4z square minus 2z, now it is 4z minus 2. So that means obviously the residues will change, and the residues are now 2, 6 and 2. And what you have here, there was a z here also there was a z, but that z has been manipulated as z inverse z square, so that this total becomes a square term, and due to this you get this particular term k 6 k 2 to the power of k, and since there is the z minus 1, this becomes k minus 1 to the power of k minus 1. And the other terms I hope you can understand, and this should be 1 to the power of k to the power of k, you will say, but why I have written to 1 to the power of k minus 1 and 2 to the power of k minus 1? Because due to this term you have to start at k minus 1. So you start at k minus 1, and this series works for k greater than equal to 1. So that's why these terms are also changed to k minus 1, because for k this at the same instant, so at k equals to 0, this term would not be there, and hence the entire sequence will not be present. So that is the reason. What is the stability criteria? So you know there is a very famous stability criteria in Laplace transform domain for continuous time system, that the poles of the transfer function must be in the left half plane. So is there a stability criteria like that for Z transform for Z transfer functions? So you look at this sequence that we have come out with, and this is, supposing this is Hz, which is the pulse transfer function, and this is the impulse response. Then you see that if we can represent it as a partial fraction, and we can actually write down the sequence like this. Now the question is when this sequence will be converging. That is the question. So if you can answer this question, you have found out the um, uh, found out what would stabilize the system. So you notice that for yk to be tending to 0 as k tends to infinity, we must have all the ai's less than 1. So we must have all the magnitude of ai's to be less than 1. Only then as k tends to infinity, each of these term would cancel out to 0, otherwise it will not. So what does this mean? This means that all the poles of in the complex plane must lie within the unit circle. The poles are ai, they are less than 1, that means the poles must lie within the unit circle in the complex plane. So whatever was lying in the left half plane in the continuous time case, so the poles now have to lie within the unit circle for the discrete time case. The relationship with the Laplace transform. So this is the last part of this lecture, relationship with the Laplace transform. So what we want to do, we want to find, so there is this sampled signal xst. If you take the Laplace transform of this sampled signal, then what you are doing is basically you are multiplying this signal with e to the power of minus kst, because you are multiplying with e to the power of minus s, right? For any function you are multiplying with e to the power minus s and then integrating in order to find out the Laplace transform. So this is the function. Now you multiply it with e to the power of minus s. What happens? This delta into e to the power of minus s gives you this thing. This is the e to the power of minus s sampled at exact instance kt. Okay, so you get that, and hence this is the Laplace transform. Now the Z transform is this. The Z transform is this, right? So if you want to have both of these same, the Laplace transform and the Z transform same for a sampled signal, of course we are talking about sampled signal. So for a sampled signal you want to have the Laplace transform and the Z transform same. So or in other words, you want to say that the idea of Laplace transform for sampled signals is same as Z transform of sampled signals. The idea of Laplace transform for sampled signals is same as the Z transform of the sampled signals. So if you want to say this, then by looking at these two equations you can easily see that your Z must be equals to e to the power of s capital T, where capital T is the sampling period. So this gives us a very important understanding, very important relationship and very important understanding. When we take s equals to j omega, that means we are concentrating on the imaginary line. Okay, so this is the j omega, this is the imaginary line. s equals to j omega we are taking, then j omega t, suppose so this is s equals to j omega, so this becomes e to the power of j omega capital T. Capital T is what? 2 pi by omega s, 2 pi by omega s, omega s being the sampling frequency. So what you are getting is 1 angle 2 pi omega by omega s. Okay, so when you are taking a section omega s by 2 to minus omega s by 2, when you are taking this section, so you take omega s by 2, put in omega, what you get is pi. So you are actually getting from minus pi to plus pi. So if you take this section from minus omega s to omega s by 2 to plus omega s by 2, if you move in this direction, then if you move in this direction in the s plane, then in the z plane, where you are moving in the z plane, this is real z, this is imaginary z, you are starting from minus pi in the z plane, moving in the anti-clockwise direction, coming to plus pi, and the circle and the radius of the circle is 1 unit circle. So this is what you are doing. Okay, so so what happens is, every section of the j omega axis, which is integral multiple of omega s, maps into the unit circle. So this is a section, so this entire left half plane is mapped into the unit circle. And if you take another multiple of omega s, so if you suppose next you take minus omega s to omega s, then minus 3 omega s by 2 to plus 3 omega s by 2, so you will be covering this such strips of the left half plane and mapping it into the unit circle of the z plane. So the entire left half plane of the s plane is getting mapped into the unit circle of the z plane. So that is an important idea to capture. So this will of course mean that the stability criteria of the poles being on the left half plane in S plane now becomes the poles being on the inside the unit circle in the Z plane. This already we have discussed. Now it comes with the relationship with Laplace transform. So now you see that, straightforward to know that to note that if you let z equals to the power st, then the Laplace transform of any sequence becomes the z transform of the same sequence. So this is already highlighted in the last slide also. So the Laplace transform of any sequence becomes the z transform of the same sequence. So with this I end the lecture, and this covers the frequency domain aspect of discrete time systems. So whatever is as part of the course is covered. There is a lot of study on discrete time systems, entire books are written, but within the purview of this course you need to understand this much only, and this is the vital information about discrete time systems in frequency domain with the help of Z transform. The vital information is the relationship of Z transform with the S transform, the stability criteria of the poles being within the unit circle, how you can actually break down the signal as a power series, as well as sum of partial fractions. Then the idea of discretization, digitization, sample and hold, all these things. So these are the important concepts you need to have with you. Okay, and of course remember this Shannon's sampling theorem. So how what is the limit of sampling that you are allowed to do. Okay, so in order to retrieve the vital information about the signal, in order that you don't lose any information about the signal, so you have to maintain a sampling frequency fast enough. So what is that, you have to understand, you have to remember. So thank you for attending the lecture, and in the next lecture we would look into the discrete time systems from the state space representation point of view. So long, goodbye.